Welcome you all to another video lesson. In this video lesson, we'll look at how to use the chi-square test to test the goodness of fit of a given set of frequencies. The last video lesson, we looked at how to use the chi-square test to find out if two attributes are independent. This is another application of the same test that we check if the given fit is good enough for the given distribution. This test is valid only when the number of observations or the sum of the frequencies is at least 50, and the individual frequencies must not be too small. The frequency is less than 10, it's got to be combined with neighboring frequencies so that every frequency is at least 10. And the number of classes into which the frequencies are divided into must neither be too small nor large. We are expecting at least 4 frequencies and a maximum of 16 frequencies for the test to be giving us good enough results. We'll look at this through an example. The following table shows the distribution of digits 0 through 9. The numbers chosen from a few random pages of the telephone directory. The question wants us to examine if the digits are distributed uniformly at 5% level of significance. So the few pages that are selected, we see that 0 appears 504 times, 4 appears 501 times, 9 appears 492 times, so on and so forth. Now to test whether this fits the expectation that the digits are in fact distributed uniformly, we perform the chi-square test. So we draw the null and alternate hypothesis. The null hypothesis will be a default statement which states that the observation supports theory or that the numbers are in fact distributed uniformly. The alternate hypothesis is the exact opposite. The numbers do not support the theory that they are distributed uniformly. But what do you mean when you say that digits are distributed uniformly? We say that each class has more or less the same number of occurrences. So if they have the same number of occurrences, then the average must be consistently observed across each class. So we first find the average. We add all the 10 frequencies and divide by 10. We get 500 to be the average. So this should be observed across each class. In other words, we say that 0 should appear 500 times, 1 should appear 500 times, 2 should appear 500 times, so on and so forth, for the digits to be distributed uniformly. That's the expectation. The observation is that the frequencies are like 504, 509, 498, 504 again, so on and so forth. So there is a difference, but we'll find out if this difference is negligible enough. So we match them up against the observed frequencies. Every entry of the expected column is 500 because they are to be distributed uniformly, and the observed frequencies are given in the column 1. So we find the differences as usual by the definition of chi-square. We square the differences. We find the ratio of the square to the expected frequencies, and we add all the ratios. The ratio comes down to the ratios added to 0.676. But this is the calculated value. We'll compare this with the table value, the critical value. We have already learned that to find the critical value, we need to find the degrees of freedom. For the 10 classes of data here, because we have 0 through 9, there are 10 different classifications of the digits. The degrees of freedom will be 1 less than 10, which is at 9. So referring to the table of for chi-square, at 5% level of significance, we observe that at 9 degrees of freedom, the critical value is 16.919. So we have the calculated value at 0.676, the critical value at 16.919. Comparing the two, we see that the calculated value is less than the critical value, therefore it falls in the confidence interval, and that is enough evidence to show that H naught must be accepted. Or in other words, the digits are distributed uniformly. That is sufficient evidence to show that the digits are distributed uniformly. The next problem is one of a kind, based on an actual biological theory. The experimental results by scientist Gregor Mendel predicts that the seeds of a certain plant can be classified into 4 types: round and yellow, round and green, wrinkled and yellow, wrinkled and green, and that these seeds are in the ratio 9:3:3:1. The theory predicts that the seeds are distributed in this ratio 9:3:3:1 for the four types. To validate this theory, an experiment was done where 800 seeds were collected. We have classified them into the four types. And the number of seeds in each category comes down to 455, 148, 153, and 144, and just 44. And we're going to check if this experiment supports the theory at 1% level of significance. The null hypothesis again is pretty straightforward. By default, it is framed in such a way that the experiment supports the theory. That is, the seeds collected are in the ratio 9:3:3:1. And the alternate hypothesis will be the opposite of null hypothesis, that the experiment doesn't support the theory. So we just calculate the observed frequencies and move forward. To find the observed frequencies, we see that their total number comes to 800. I have given the names A, B, C, and D to the four types. Round and yellow is A, round and green is B, wrinkle and yellow is A, wrinkle and green is B. So their total number is 800 as per the question. But the ratio that is expected is 9:3:3:1. The four numbers have to give us 16. So when you express the ratio in terms of fractions, it's 9/16, 3/16, 3/16, and 1/16. That's going to help us calculate the expected frequencies. We find what is 9/16 of 800 is 450, 3/16 of 800 is 150, and 1/16 of 800 is 50. So we have the observed frequencies at 455, 148, 153, and 44. And the expected frequencies at 450, 150, 150, and 50. So we calculate the differences, we square the differences, we find the ratio. The ratios add to give us 0.262. That's the calculated value. Now we compare this across the table value. And since there are four classifications here, the degrees of freedom is 3. And therefore, we refer to the table and we find that at 1% level of significance and 3 degrees of freedom, the table value is 11.345. So comparing the calculated value versus table value, we observe that the calculated value is less than the table value, and hence there is enough evidence to accept the null hypothesis or state that the experiment supports the theory that the ratio of seeds are in fact 9:3:1. The third problem is interesting in two aspects. 5 dice were thrown 243 times. The number of times 3 or 4 was observed are given below. The experiment shows that out of the 5 dice, 3 or 4 were recorded 0 times at 30. Exactly one of the dice showed 3 or 4 72 times. Two of the dice showed 3 or 4 74 times. Three of the 5 dice showed 3 or 4 51 times. Four of the dice showed 3 or 4 14 times. And all the 5 dice showed 3 or 4 2 times. Now, we'll examine if this presents us with enough evidence to show that the dice is unbiased. So, as usual, the null hypothesis will be that the dice will be unbiased or the experiment will support theory. And an alternate hypothesis will say that the dice are biased. What do you mean when you say the dice are unbiased? All 6 numbers have an equal probability of showing up. The probability should be 1/6 for 0, for 1, for 2, for 3, for 4, for 5, and for 6. Now we are focusing only on 3 and 4. So this gives us a two-way classification of the outcome. So the numbers are either 3 or 4, or they are not 3 or 4. So this two-way classification points us towards binomial distribution, and so we will find the expected frequencies using binomial distribution. So a 3 or 4 will show up with the probability of 2/6, that's 1/3. A 3 or 4 will not show up with the probability of 4/6, which is 2/3. So this helps us model the expected frequencies using the binomial distribution, where n is 5, the number of dice that are used, P and Q are at 1 by 3 and 2 by 3, X ranges from 0 to 5. So to find the expected frequencies, we do this small calculation. First, we find the probability that X is either 0 or 1 or 2 or 3 or 4 or 5. And we multiply each of the probabilities with the total number of times this experiment is done. That is 243. So 243 times the probability will give us the expected frequency. So if x is 0, we have 5c0 times 1 by 3 to the power of 0 times 2 by 3 to the power of 5 as the probability. That simplifies down to 2 power 5 by 3 power 5. Multiplying that by 243 returns the number 32. We'll repeat this for x is equal to 1. So that's 5c1, which is 5. 1 by 3 to the power of 1 times 2 by 3 to the power of 4, which is 80 by 243. When we multiply this probability by 243, we get the number as 80. So repeating this, for x is equal to 2, we get the answer as 80 again. For x is equal to 3, we get the answer as 40. For x is equal to 4, we get the answer as 10. And for x is equal to 5, we get the answer as 1. So these are the expected frequencies. And now that we have both the sets of observed frequencies and expected frequencies, we can proceed further. There's one glitch though. We observe that one frequency in both columns is less than 10. In the observed frequency, we have a number 2, and in expected frequency, we have a number 1. Both these are less than 1. We saw that for the test to be effective, we need all the frequencies to be at least 10. So to ensure that the frequencies are at least 10, we club them. So 14 and 2 are clubbed to get 16, 10 and 1 are clubbed to get 11. Once we get these, we have only 5 classes. The first 4, all of them which are greater than 10. The last 2 which are being clubbed as 1. So 4 plus 1 is only 5. So 5 observed frequencies versus 5 expected frequencies. We do the routine. I've highlighted in red the last row of the table, which denotes 16 and 11, the club frequencies for both kinds. So we calculate the differences, we square the differences, we do the ratio, and we add the ratios. We find that the chi-square takes up a value 6.672, is the calculated value. Not the tabulated value here. This is the calculated value. So the calculated value is 6.672. Now we compare this with the tabulated value at 4 degrees of freedom. Remember, it's not 6 minus 1, it's 5 minus 1. We have clubbed the last 2 classes. So that's 5 minus 1 at 4 degrees of freedom and 1% level of significance. Looking at the table, we see that the tabulated value is in fact 13.277 at 1% level of significance. So the calculated value is at 6.67. The tabulated value is 13.277. We observe that the calculated value is less than the tabulated value, which means X naught is accepted. We conclude that there is enough evidence to say that the die is in fact fair or unbiased. So that gives us enough practice on understanding how to use the chi-square test when you test the goodness of a fit. And follow this video with another video on a different set of problems shortly. Thank you.